give part.
Okay, algorithm and complexity. Okay. And Paramita,
Second method.
yeah.
Okay. So
So
Like
you are
how was your
for
quiz one?
determinant one. For
determinant.
1 cross 1, it would be 1. For 2 cross 2, it would be 0.
Yeah.
So
For
that's why it's
one.
semi-definite.
Yeah.
Yes,
Okay.
there is important. So if it is -3, then it completely
Oh, yeah.
fails.
You have no. Yeah. You have to calculate all.
Okay. So we are starting the live coding session. Oh, I'm sharing the screen. Just wait. So you all, I think you have already joined the Replit team, or anyone want to link of this team?
Yes, sir. I can.
You have already joined, na? Okay, okay. Okay, I'm sharing I'm publishing the problem one.
Please share the link, sir. Actually, I
Oh, link. Okay, okay. Just wait. Yeah, so I've pasted the link in the chat box. So if you're not joined this Replit team, so you can join from this link. Okay. Okay. So I'm publishing the problem first, which is related to the big five. So we have six problem today. Three from the big five and three from big six. So we will try to solve all the problems today live session. First problem, yeah, I published the problem number one of big five. So you can start to write the code for this problem. What is the problem is? Yeah, so this is the problem statement. So what we are asking in the problem statement, an airline company wants to make airport to connect n cities labeled 0 to n-1 all across the country. Okay, write a function airport. There is one parameter distance underscore map that accept a weighted adjacency list distance underscore map in the following format. So basically what we are providing as an input in the airport function, we are providing a adjacency list in the dictionary format. Okay, so where the key is representing the source vertex and the value is a collection of tuples in list, and every tuples contains the destination vertex comma distance from source to destination. Okay, so this is the information we are getting in the input as a dictionary. So what we are return, so what will be the return? The function returns the minimum distance of airport network to connect all entities. So this function will return the minimum distance of airport network to connect all entities. So here one example is given. So for example, this is a graph. Okay, so in this graph where we have a vertex which represent the source, uh, which represent the city, and the distance is h weight is represented as a distance in kilometer. So input format is in this format. So first value is in the input is represent the number of vertices, and second value in the input is represented the collection of edges in the graph. Okay, so after getting this input, so we are creating a adjacency list in a suffix code. So you can see the suffix code in the code in your code part. So this is the suffix code. One second. Okay, so I have to change something here. One second. Okay, so I think suffix is not proper for this. I'm corrected it. Just refresh your code problem statement. Okay, now this one. Okay, I'm sending the link again in chat box. Yeah, so this is the Replit link. You can join this team, Replit team, by click on the link. Yeah, so in you can see the suffix part where we are getting the input in. So first line is representing the number of vertices, and second line is representing the collection of edges. After that, we are creating a adjacency list using this information, and we are providing this adjacency list as a input in our airport function. So after that, you have to write the code for this. How you can find the minimum distance of airport network to connect all entities. So
We can use a Dijkstra algorithm.
yeah, Harjit, sorry.
We can use the Dijkstra algorithm.
Digester algorithm. Okay. So can you tell me what is the purpose of digester algorithm?
To find the minimum distance.
Find the minimum distance.
Yes.
So find the minimum distance from source to destination.
Yes.
Okay. But here, what we are asking the total network distance. That should be minimum.
Okay.
The function returns the minimum distance of airport network to connect all entities. So here we are asking the total distance of network. That should be minimum.
Okay.
Using digester, we find out the shortest path or shortest distance from any particular source vertex to other destination vertex. But here we are not asking this information. We are asking the information, the total distance of the network, which should be minimum. So this type of information we can find out using the minimum spanning tree concept. So you can apply the algorithm which we used in the minimum spanning tree algorithm. So like a Prim's algorithm or Pascal algorithm you can apply. Okay, just try. So I'll explain in more detail after 5 minutes. So before that, you can try. Yeah, Bimlesh, actually we are trying to extend this for the deadline of some part of the assignment, like a programming assignment of the week 6, but still we are not sure. So maybe we will extend the deadline for week 6 programming assignment. I think for 3 days only. Okay, Bimlesh. Week 5 GRP, I'm not sure because we have already given 2 weeks for the week 5. Okay, week 5 have already released before the quiz, and we have already extended 1 week for the week 5. But so maybe week 6, the maybe deadline. Okay, done. Can you send announcement text? Okay. Just wait, I'm checking that. I think deadline for week 6 have already extended. Yeah. So week 5 deadline have already extended. Now deadline is 15 June. Okay, I'm checking for the week 5. Yeah, that is today. Okay. So yeah, for week 6, all type of assignments, graded theory as well as the graded programming. Now deadline is 15 June. Okay, so how many of you have started? Yeah. Yeah, so if you have any doubt to understand the problem, then you can ask what is the problem, what the concept we can use to solve this problem. This is a simple, straightforward question. Here we are asking the shortest distance network. So not shortest, so minimum distance network. So that can be solved using the minimum spanning tree concept, and we can use any of the one of the algorithm like like Prim's or Crystal algorithm we can use to solve this problem. Yeah, so Harshit, can you refresh your problem because suffix is not updated in your code.
Sir, I updated. I refreshed the portal. Is it?
But okay, still the suffix is not updated. Okay, I'm changing the suffix in your code. Just wait. Okay, now I have updated. Now you can write your code. Okay, so how many of you have completed? So if you have completed, then you can send a message in the chat box. So I can see out of two, three, this is one thing. Okay. So remaining ones participants, only 5 have started the problems. Remaining can also start to solve this problem. If you have the link of the Rapid team, you can join from there. Otherwise, I'll paste the link in the chat box again. You can join the Rapid team. Yeah, so I have pasted the link again in the chat box. You can join this Rapid team using this link, and you can start to solve this problem. So I've already given some idea how we can solve, which algorithm we can use to solve this problem, because so this is the problem statement. So there is so we have a graph in the form of this adjacency list as a dictionary, and we are asking to find the minimum distance of airport network to connect all n cities. So this type of information from graph we can use the minimum spanning tree algorithms, and we can directly use the any one of the algorithms, like Suprem's algorithm or Crystal algorithm. So you can write your code here. So I think some are trying in the correct way. Restricted as distance. Okay. Okay, so I'm explaining the solution for this. I'll use the Kruskal algorithm for this. So those who are facing difficulty, they can see here. So this is my okay. Okay. So we will write the function. Therefore, and we are getting a list WL. Super example. I'm not sure the solution will change. I think. Okay, just wait. Okay, so yeah, Vimles, yeah, you are not writing any solution, so I am writing the solution in your replit now. Okay, so what we will do, we will so here we are getting an adjacency list. So in Kruskal algorithm, what is the concept? In the Kruskal algorithm, we first step is we will sort the edge in increasing order of their weights. So before that, we will okay. So we will create a edge list. Edges empty list, and we will make a loop. So for we will read all the edge information from the adjacency list. So for example, so for I E in double
Excuse me, sir.
sorry, is this?
Harshit.
Yeah, Harshit.
Sir, actually, the function name is airport, a distance name, right? A distance map. Okay.
Sorry.
The functions name here, line number 1, you are taking airport WA, and
Okay.
the functions, write a functions name distance map. So can we take as a distance map instead of WL?
Yeah, you can take any. You can take any name. So in our question, actually, 1 second.
But yes, we have to return in WL in line number 16, right?
So this is the suffix code actually. We are receiving the input in these two parameter. After that, we are just inputting this WL list as input. So
Okay.
both are the same things. We can use any parameter name. In column statement, distance map name is given. Okay, no issue. But actually, we are creating a this adjacency list in our suffix code. So here actually we are using the name WL. So and we are passing the same WL list in the airport function. So no
So
issue. We can
we have
use.
okay.
Okay. So this is what so so we'll read the key from the WL adjacency list, and for every key, so for E in WL, okay. So there we have to create one more loop. interview. So for so this is the U information and this is P comma D. And so of U. And after that, we will append this information in our list. H is dot append in the tuple format. Okay, so first we will take the distance D, comma U, comma V. Okay. U, comma V.
Sir, there is an indentation, so line number 5.
Line number
4.
5. The indentation is okay, I think.
Line number 5, sir.
Mhm.
Ages dot append. Right.
Okay, yeah. Then after that, we will sort this list. So edges dot sort, and then we will check that what we are getting now. So print edge. Okay, so we will run this code. Just take one sample input from here. So for example, size equal to 7 and edge information is given here. We will change this later. Int object is not retrieved, line number 18. Oh, sorry. This is edge. Yeah, so this is the list. 1, 2, 3, 4, 5, 6, 7, 8, 10. Okay, so one is the print test and okay, is here. So every S is W list weighted list. Okay. So the okay, we are getting the 1S 2 times here because 0 to 1 and 1 to 0 both we are repeating here. Okay. So how we can remove these things? Because we want to take S only one times in our edge list. So we take the condition of the discrete. sort of thing. If okay, so if v comma d d comma u comma u plus d d comma v comma u not on x. Yeah. Okay. So yeah, so from the adjacency list, actually in the adjacency list, we are storing the info one edge information two times because this is an undirected graph. So one edge is considered by from both. So for example, there is one edge between U and B. So we are storing first U as a key and then B as a destination, and second V as a source and uh, V as a source and U as a destination. So two times. So we will filter out this. So we will mark the one edge only one time in our edges list. Then after that we will sort these edges. So we are getting the correct information. Now we will apply the classical algorithm concept. We will take the edge one by one. If edge is creating a cycle, then we will not consider this edge in our final network. Okay, so before that we will create some initialization. So for example, there is a cost. We will first set for the cost equal to 0, and second is one is component. So the component we will create a dictionary here for the component, and for component, so we will initialize this component value for every vertex in our network.
Sir, a small doubt. Why we are taking the nested list in line number 4?
Line number 4 here.
Yes, yes. Why
Yeah,
we are taking
actually,
this?
so for U in WL, actually here we are reading the key in our adjacency list, which are representing the source vertex. After that, we are
Mhm.
reading using this loop, we are reading the value of each key.
Okay.
Okay, so for example, in adjacency list format, if you see the problem statement,
Mm-hmm.
so this is the format of adjacency list. So every source vertex contains a list of edge information in our adjacency list. So for by first loop for U in WL, we are accessing this key source vertex one by one, and
Mm-hmm.
for each vertex, source vertex, we will read the all edge which are connected to this source vertex. So we will read this list information in our adjacency list. So V comma D. So here actually there are two parameters in each tuple. So
Mm-hmm.
destination index comma distance. So we are reading this information in V comma D
Mm-hmm.
in the from in this list. So after that we are creating a edge list. So here we have so we mark one condition for remove the duplicacy of edge, and we are appending this edge information. We are taking distance at the first position because we will sort this tuples list.
Mm-hmm.
So this tuples list will be sorted by the first parameter in increasing order. So we are creating a edges list here. So we will get all the edge information, and then we will sort it. So we will get the sorted list according to their weights. After that, we will take the edge one by one, and we will mark this edge in our final graph. If it is creating a cycle, so we will not consider that according to the critical concept.
So this line number 5 condition, how is it checking? Because initially when it is traversing through the adjacency list, DVU will not appear, no?
So for example, first what we are doing here, so UVD. So for example, there is so one S 0 1 10. For example, this S is inserted first time. So we will check that. So here U is 0, V is 1, and D is 10. Correct?
Yes.
Okay. So for example, this edge is not in our edges list. So in the first condition, we will check this 10 comma 1 comma 0. 10 comma 1 comma 0 not in our edge, so this information will not be available in our edges list. So first time this DUV will be added in our edges list.
This
But
edges, not in edges, is this edges is a input already taken, correct?
yeah, this is a suffix code, but in our for our function we are getting this WL information only, so we will not use this edges directly.
Can we rename our variable like edges underscore
Oh, okay,
if
okay.
in the
So
line
you are
number 2?
okay, okay. You are confusing with this. Okay, so edge. So edge list. Okay. Yes, actually suffix code is visible for you, but in according to the problem statement, we are getting only one input distance map. So we can also change the name of this because it is also creating some confusion. Okay. Now we are getting this distance map as a WL, and then we will start. So edges list dot sort component. Now we will initialize this component value for every vertex. So for U N W L, so component of U equal to U. Okay, so this is the first initialization. After that, we will read all the edge one by one. So for example, so for each edge, so we will read each edge. So in our edge, so first value is distance, second is U source vertex, and third is destination. Okay. So for D comma U comma V in edges. Edge list. If then we will check that this edge is creating cycle or not. So how we can check this using Pascal algorithm? So we will check the component of each. So component of here U and V. So we will check for U, and a component of U equal to component of V. Okay, so we will add the S if the components value is not equal for U and V. So we will mark the condition here. Okay, so if components value is not equal, then that means this edge is not creating a cycle. So here we will read the component value, which is equal to component of example U, and same time we can add the cost for our output. So because if this condition is not true, we will add this edge in our final output. So cost equal to cost plus D. Okay, because we are asking the minimum cost, minimum distance total. So we can mark this DIST. DIST. Okay, so DIST. Okay, so C equal to component A. Then we will read so component. Okay, then we will. Okay, so for okay, so for vertex, so for V and then if that is in the okay, so C. So we are marking that over vertex and component of U. So after adding this, we will update the component information. So we will read all the keys here and see. Okay, if okay, so component of V equal to so component of, so yeah, this is also we have already used, so like text text, then if it match with the component of V. Then we will update the equal to C. Okay. And in last, we will return the cost. Sorry, this okay. Check that what we're getting. 307. Something is wrong. 307. Let's check what is the wrong. things. U does not equal to component of B, this equal to this plus D. D, okay. And C equal to component of U, W, L. Or vertex W, L, component of vertex. This information. So we have to debug these things. So in the first part, 0, 1, 2, 3, okay. This is okay. Component is not updated. So for example, the first is so first as will come from here. So 0, 1, 0 is U. So components are not same. So 0 and 1 are not same. Then we will copy the component of 0 in C. Okay. And for vertex in WL, we are writing the key and checking that if component of vertex equal to component of V, this is only one. And we update this information. This is updated. For the second edge, 2 and 4. So I think some critical part we are missing here. Okay, so I'm opening the second problem. If you have already solved this, you can start other problem. 1 second. 2 and 3rd. Okay. So D. Nice. First is 10, 20, 30, 37, all I did. 30, 30 also edit. So for example, we have a edge 1, 2, 6, so 0 to 6. So 0, 1, 2, 3, 4, 5, and 6. So first we will add this 0 to 1 edge. So 0 to 1 edge we will mark, and our weight will be considered here. And component value we are also marked 0, 1, 2, 3, 4, 5, and 6. So first thing 0 and 1. So we will mark, change the component here like 0. Okay, after that we will take the second edge 2 to 4. 2 to 4. Okay. So we have this one. 2 to 4. So this is 20. Component are different, so we will consider this. And we will change the component value. So we will receive 2 and we will update this by 2. Okay, so this is okay now. Now 31, 2. So 1, 2. So yeah, this is 0 and this is 2. We will add this. And this is 30. After that, we will read the 0 value. And we will check that what is the value of component of 2. So this is 2. So we will update this by 0. This is also 0. This is also correct. And then 4, 6. So 4, 6 is this. Component value is different, 0 and 6. So we will add this. So this is 37. And what will be the component value of now 6? So this is 4, 6. U here, okay. Okay. 1, 2, 6. 1, 2, 3, 6. So we will update this value by 0. Now 6, 1, 3. So 1 and 3. Yeah, so this is also become 0. So as we'll consider 40. And there is also one more 5, 6. So 5, 6 is also there. Okay, so yes, 5, 6. Okay, so 5, 6. So now we are getting the value for 5. We are getting from the 6. 6. Let's update all the. This become 45. 0, 2. 0, 2. Now everyone has the same. Okay. We should Now 10 plus 20 plus 30 plus 37 plus 40 plus 45. This should be the answer. A concept is looking very. So can anyone identify that where we are wrong in this code, because concept wise is looking correct. So 10 plus 30 plus 60, 60 plus 97, then 45. Then how the 60 is at 60 and 65, 3 to 4. So 3 to 4. So 10, 20, 30, 37, now 40, okay, 45. After this line, 0, 0, 0, 0, but here 2, why it is not change? 6. It is not equal to 10 centimeter equal to C. It's equal to 1.2. Just getting confusion. So to be this. Okay, so I think some error is anywhere. So just wait. Let's see. Okay, 'Okay, now it is correct. Okay, so just check the test case. One is failed. It should be 36. So 6. 36. Okay, so due to this print statement, We'll remove this part. So this is important actually. Yeah, past. Okay, so some components are not updating properly, because of that the issue was coming. Otherwise, this is a critical approach. So here basically what we are doing, we are first we will sort the edge according to their weights. After that we will take edge one by one, and we will add the distance of, if we are considering the edge in our final output, so we will add the distance for our output. So for checking the cycle, we are using these component methods which we used in our classical algorithms. So if components value are same for both source and destination, so that means both vertex are belongs to the same component. So we will not consider that edge in our final network. So using this condition, you can find out the cycles, if edge is creating cycles or not. Otherwise, we will consider the edge in our network. So after considering this edge in our network, we will update the components value of which. So after connecting, for example, we are connecting. So like this graph, if we are connecting this edge 1 and 3 in our graph, so we will read the value of 1. What is the component value of 1? And then we will update this component value. So for example, 3 is connected, 3 is not connected to any other vertex. So this vertex value is initial by 3. So we will update this component value 3 to 0. So that will represent the same value represent the same components. So if vertices are connected to each other, so those vertices will always contain the same component value. So using this concept, we can solve this problem. So okay, so we'll move to the second problem. We have already more than 1 hour. Yeah. So second problem is also related to the same concept, but here we are asking. So what is the question? An airlines company has flight operation in n city level 0 to n-1. Write a function best fare. There is so some information is given: flight route, source, destination, and k value, in which you are given a weight adjacency flight route in the following format. So same thing. So we are getting the same information in adjacency list in the dictionary format. After that, what we are asking, so you are also given 3 integers: source vertex, destination vertex, and k. So this is representing a positive integer. So this is a positive integer value. And function returns minimum cost and flight route in the format minimum cost, comma. Okay, so there is one list. So inside this list, we are representing a path, source to destination, from source to destination. So there is one condition is given here: from source to destination with at most k stops in between source to destination are not included. Okay, so for example, if we are asking, so for in given graph, we are asking to find out the shortest path from 0 to 4. with at most two stops. So at most two stops means in between we can allow uh, at most two at most or at least maybe okay, at most k stops. So we will consider
So,
the yes.
so stop can be direct flight like zero stop, one stop, and two
Yes, yes,
stops.
yes, yes. So at most maximum number of stops. So we are asking if k value is 2. So we will consider the direct flight 0 to 4. If there is one stop, that will also consider. If there is two stops, so that will also consider. But more than two stops, will not consider in our path. So here I think in the code, so some sub prefix code is also given. So you can use the output of this prefix function. So this prefix function basically providing the uh, find all paths. Okay. So this find all path returning the all possible path from our graph from source to destination. So after getting these all paths, you have to write the code uh, according to the problem statement. So for this problem, what we'll do, so here, first thing, so in our main function west, where fly to source destination k. So from source to destination, we will call the this find all path function, and we will get the information of all path in our list. So we will directly, so this is my, okay. So I'm using this time, I don't know what is the object name. Okay, so we will call this our already function is given in the prefix find all path. So for example, path equal to find all path, and we will pass this w list information. So this is applied to this is first information and source comma destination. Okay, so where I okay, so here we are using this function. So this function will return all the path in the list format. So after getting this all the path, we will check that what we are getting. So path.
Sir, what algorithm should be used? Is it DFS or some other?
No, so for this person, I think no specific algorithm is required, because we have already getting all path information from the given prefix code. After that, you have to just find out the path which are for, which are satisfying the condition given in the problem statement. All. So, for example, you can see here. So I'm just printing the path what we are getting from our this function. So we are taking one sample. So this is the main. Yeah. So for example, the size is 5, and age information we are getting from here. Okay. Okay. So 041. 0. This is source. This is, for example, 4 destination, and this is stop value 1. Okay, so I will test this what we are getting now. Yeah. So this find all path function, which this is providing all the possible paths from 0 to 4. Okay, so 0, 1, 3, 4, 0, 2, 1, 3, 4, 0, 2, 4, 0, 3, 4.
Okay.
Okay. After that, what is the condition? Condition is that we can accept the path which contain at most one stop. Okay, so at most one stops. So is there any available? At most one stop. So there is one. This is 1024. Okay, and 034. So there are two paths available with this condition. Okay, and remaining one have more than one stops. 0, 1, 3, 4. So this contains two stops, and 0, 2, 1, 3, 4. This contains three stops in between. But but maximum possible stops should be only one. So there are two paths we have received from this find all path that satisfy this our condition, our problem statement conditions 024 and 034. Okay, so we will check only for these two paths. What is the cost of these two paths, and which one is the minimum cost path? Okay, so after getting this information, we will read all the path information in our path list and check that. So for example, for p and path, so we can create a okay, cost was cost. So here we will take one cost value. So we will just initialize by this cost equal to, for example, I'm creating the one highest value, so we can just initialize the infinite value in Python, like so inf, so in float string में inf. Okay, so for p in path, if length of p is greater, smaller, equal to, so k plus 2. So one k is the stop number and one is source and one is destination. So total number of value elements should be in the list, should be in the path, should it should be less than equal to k plus 2 plus 2. Okay, so this is the condition for the path selection. So for p in path, we will read all the paths from the path list, and if the length of the p is less than equal to k plus 2, we will check for that. So okay, so we'll check the cost for it. Okay. And cost is given in our adjacency list flight route. Okay, so what is the format of flight route is? Flight route, source index and destination index. Okay, so we will check that what is the source to destination and what is the price. For path, for people path. For vertex B, vertex and P. For vertex in P, okay, so this is this one path we are reading this, and we will start from the case. So okay, so for now we will read all the destination value in our adjacency list. Paths to destination to what is cost. Okay. So okay, just wait. We have to check the logic here. Path. Vertex in P. So for example, I am range of P. So here we will check the path information. What is the price for this is 0 to 1. Okay. What you will keep the value for okay, light route. J, P. Path over to PHP. So some steps is so actually what we are want to do is, so for example, if we have a path, so 0 to 4, so we will find out the price from 0 to 2 and then 2 to 4. And so this information is given in our flight route. So for 0 key, and we can see the destination 2, price. We will read this information, then 2 to 4 price. This is the other information. Okay. So this one T minus one, 4, 3. So we will check the cost equal to price. Is price equal to price equal to, let's check the flight route, or path. That is a P I P I this flight route. J bomb. So, okay. If J equal to P I plus this price this so for ventures, okay, so by species. So this is looking for the one path. And now we repeat this part. Okay. So if this P price value is less than cost, then we will assign cost equal to price. And when we will take the more factor, let's RPS come to okay. And Yes, path equal to P dot copy. First is cost. And second information is yes, path. Zero to four. The print statement is there. Yeah, so this is the solution 2500024. Okay, according to the problem statement, what is the answer? Yeah, this is correct. Just check the test, please. Oh, fail. Not found. Okay, so we have not given one condition. So if path is not available, then we will return the not found message. Okay, so last. Yeah, so this is the concept basically. So we will add one more condition if path is not available with required number of steps. So we can directly return the none as the answer. So for example, if not found as the answer. So according to the problem statement, if there is no path available with the required number of steps, stops in between, so we will return the not found. So we can apply this condition in this place. So for example, we'll check that for example, if rest path, if there is no path available, for example, there is no path returned by this find all path method. So we will check this condition. So we'll directly return that not found. Or after that, we will check one more condition. If there is no path available with required number of stops, so also we will not we will return the solution not found. So after modification this part of this part, we can get the solution for this. So this is the exact solution. The same things we are using in the solution. So after getting this all path, we will check that if L does not equal to empty. So if L is not empty, then we will check the best path. If L is empty, then we will return not found in this else. Same things. We will check here the second condition. So yeah, so we are taking one root list and we are reading all the paths from the list. If the path length is less than equal to k plus less than is k plus 3, then we will check the cost for that path. If the cost is less than the previous path cost, previous cost, we will update this information, and we will also update this route information. For example, after completing this process, if our route is empty, then we will return not found. Otherwise, we will return cost and route. So using this concept, we will test this. So this will run all the tests. Oh, okay. Actually, we have update our. We have to change this part. So it's okay. So for the third column, yeah. So this is transitive closure. What is transitive closure? So the definition is given for all I comma j pair of vertices in a graph. Transitive closure matrix is formed by the reachability factor. So for example, if j is reachable from I, means there is a path from I to j, then we can put the matrix element as 1. If path is available from I to j, then we will put the 1, otherwise we will put the 0. Then we can put, if there is no path, then we will put the 0 in our matrix. So this reachability matrix is called the transitive closure for a graph. So here we have to write the transitive closure function for given gmat. So this is the input adjacency matrix we have given. So that accept a matrix gmat as a nested list for a directed and connected graph where gmat I comma j equal to 1 is represented that there is an edge from I to j or I equal to j. Okay, so same vertices to same vertices, we will mark the 1 value here in this matrix, input matrix. Otherwise, if gmat I comma j equal to 0, that means there is no path from vertex I to j. So for example, for this given graph, so you can see this matrix. So for example, so 0 to 1. So 0 to 1. So this is actually in the list format. It will be present as a matrix format. So you can see this. Okay, so row is represent the value I and column is represent the value j, and this one value is representing there is an edge from I to j, and 0 is representing there is no edge from I to j. So this is the input, and our function should return the transitive closure for that. So we can use the float Warsaw concept in this column. So here information as present information is given in the format of 0 and 1 value. So so for this 0 and 1 value, we can apply the AND or logic for this value. So for example, for this input, so this information is given 0, 1, 2, 3 and 0, 1, 2, 3. So 1, 1, 1, 0, 0, 1, 1, 0, 1, 0, 1, 1 and 0, 0, 0, 1. So this is the input matrix for the given graph. After that, how we can create a transitive closure for that. So we will apply the float Warsaw algorithm. So for example, what is our graph? So just wait. So here 0, 1, 2, so I create a clear graph for this. So 1, 2, 3, 4. Okay. So there is one is yeah. So for transitive closure, we will check that. So we will create a new matrix here 0, 1, 2, 3, and 0, 1, 2, 3. And using this information, first, so first we will check that for example, for to fill this field 0 to 0, 0 to 0 is always 1. So okay, so we can directly fill this information like 1, 1, 1, 1. Okay. Because this is the already filled one. Same node to same node, so no need to check for this. But 0 to 1, okay, so 0 to 1 we will check that is there any for so we have to create for there are 4 vertex, we have to create 4 matrix to solve this. So in for the first case, so we will check that is there any path is available from vertex 1, sorry, for vertex 0 or not. So for example, we will check that there is path from 0 to 1 is direct available or not. So yes, so 0 to 1 is directly available. So we will check is there any path from 0 to 1 or 0 to 1 or 0 to 0 then 1. So this is the middle field. This value is dependent on the matrix. So if we are creating a first matrix, we will take this middle value as a 0. For the second matrix, we will take as a 1, then 2, then 3. Okay. So first, in the first condition, we will check that 0 to 1 directly edge is available or not. Or if this condition is not true, then we will check the second condition. 0 to 0, then 1. So for this matrix, this middle value, for example, this value is k. So here for this matrix, we are taking this k equal to 0. So we will apply this formula on for calculating each cell value. So 0 to 1, so we will check that 0 to 1 value is 1 or not. So 0 to 1 is 1. So any one condition is true, then we will mark the true value here. So for this information, we will apply the AND or concept. So this is the OR condition. Okay. Okay. Now so then we will mark 1. Okay, we will read this one. Now for second value 0 to 2. So 0 to 2 is available. 0 to 2 is 1. Then we will mark 1. That means we can we can move from 0 to 2 directly. That means there is path available from 0 to 2 and 0 to 3. So 0 to 3 is there is no direct edge. Then we will check 0 to 0 and then 3. So this condition is also not true because 0 to 0 and then 3 there is no path available. So we will mark 0. Same things for the second 1 to 0. So 1 to 0 is now 0. And then second condition is 1 to 0, then 0 to 0. Okay. So 1 to 0 and 0 to, so there is no path. So 1 to 0 and 0 to 0. 1. So in between. So there are two conditions is so 1 to 0 and 0 to 0. So this end condition is given. So if this value is false, this is true, so all become false. So this is also become 0. Same for the 1 to 1, this 1, 1 to 2. So 1 to 2 is available, 1, 1 to 3 is 0. So 1 to 3 is 0, then we will check 1 to 0 and 0 to 3. So you can see in the graph 1 to 0. So 1 to 0 is not available. So that means this is false. So no need to check again. If one condition is false in the second case, then we will directly mark 0. So same things. We will check for the 2, 0. This is 1. Directly fill 1, 2, 1. So 2, 1. And then we will check 2 to 0, then 0 to 1. So 2 to 0 and 0 to 1. Yes, there is path available. So this is path available. Then we will mark as 1. Okay. So G same thing, 2 to 3. So 2 to 3 is available, yes. And same 3 to 0. So no path available. Then we will check 3 to 0, then 0 to 0. So that means there is no path. 0. 3 to 1. So here information is given 0. Then we will check 3 to 0, then 0 to 1. So 3 to 0, no, 0. And 3 to 2, 3 to 2, no, this is not given. We will check 3 to 0 and 0 to 2. So this is the K0 matrix we have created. Same things we will create K1 for the K1. Okay, at that time, this middle information will always as a K value. So this become a 1. So we will repeat this process total number of vertex times, and we will get this information transitive closure. So for the solution for this part is, so this is a very small port. Yeah. So here we are just reading the length of our matrix. What is the total number of vertex? After that, we are just copying a GMAT matrix in this our transitive closure matrix. So this is the same initially as a input GMAT. After that, we will repeat this process number of vertex times. So this is the K loop. After that, for each row and column combination, we will calculate this information. Transitive closure I comma j. So either this is this. There are two conditions. This there is a path from I to j directly. Otherwise, we will check the second condition. There is a path from I to k, then k to j. So if any condition is true, then we will mark as a 1. So here we are using the logical thing. So this will return a 1 value if it is true, and 0 value if it is a false. So we fill this matrix using this 3 nested loop and this formula. Then we will get this transitive closure information that will provide this information reachability from I to j. Okay, so move to the next column of week 6. Yeah, so yeah, so this is the problem. Write a function type of heap Here we are providing a array as a heap that accept a heap A and return string max if input heap is a max heap, min if input heap is a min heap, and none otherwise. So for you can see the input here, we are providing a list of elements that is representing a heap, and our function will check that this input, this is representing a min heap, max heap, or none of these. So our function will return the type of heap. If it is a max heap, then it will return the max. If it is a min heap, then it will return the min. Otherwise, it will return the none. So type of heap. So how we can check this information from the given list? Okay, so this is an input list, and how we can represent this input list as a heap in the heap format. So always first value is as a root, then we will traverse level wise. So 2, 3, 4, 5, 6. Okay, and our function will check that this is a max heap, this is a min heap, or this is a not a min or not a max. Okay, so how we can check this? So we have a list, and in our list, first element represent as index 0, 0, 1, 2, 3, 4, 5. Okay, so how we can, so for the min heap, what is the condition should be satisfied for min heap? Parent node is always be less than our child node. Okay, so we will check that every parent should be less than their child nodes. For max heap, every parent should be greater than to their child nodes. If both this min heap and max heap condition is not satisfied, that means this list is not representing any heap. We will return none. So now how we can check this info, these things in our given list? So how we can find out the left child and left right child information? So we will start. So this is a list. This is a list, and we are considering this as a heap. So we will start from the parent node, first parent node. Okay. So these are the leaf nodes. So all three below are the leaf nodes. So we will not check for that because there is no child for for that nodes. Then how we can find out the first parent node from the bottom? So we can find, so what is the total length of our list is? So total length of list is 6. Okay, and then we will divide, we will uh, we will find out the floor division value. So 2. So what will be the value is 3. Okay, so yeah, 3, 0, 0, 1, 2, 3, 4. So total length is 6. Yeah, okay, 3. Okay, yeah, so actually we will check that the third index, so 3 index. 1 second. 3 to 6. Okay, so not the length divided by 2, actually the last index,
-1
yeah, length of list -1 to division 2. Okay, so this will return the 5, and divided by 2 return the 2 index. Okay, so we will check, start from the this second index node. This is representing it, the first parent node, which contains the child.
Length of L by 2 minus 1.
Length
Length of the list divided by 2 minus 1.
-1. Okay. So for example, 6 is 7, 7.
That will take care of odd row.
So I think this should also work.
Okay.
Okay. So we will check from this second index node and we will compare the elements. If the value of this second index node is less than of their child node. So how we can find out the index of child nodes? So for example, if we are checking for this second index node, so we can directly calculate the left child value. So left child will at the index of 2. So for example, we are calculating the left child of I. Okay, so we will just we can calculate using this formula 2 into I plus 1. So 2 into 2 plus 1, this is a fifth index. Same for the right child. So right child can be calculated using I 2 into I plus 2. It is representing 6. Okay, so we will just check that the value of this ith index is less than of their left child and right child. If this condition is true, then we will move to the next parent. If this condition is false, then we can directly return this is not a min heap. So for example, if we are checking for a min heap, we will check this part is representing a min heap or not. So if this part is representing a min heap condition, this part is satisfying a min heap condition, then we will move to the next parent. So we will check for this. So for example, this part is also satisfying a min heap condition, then we will move to the next parent. So then we will check this part. If every part of our heap is satisfying the min heap condition, then we will return this is a min heap. Otherwise, then we will check if any part of this heap is not satisfying the min heap condition, then we will we will check the max heap condition. Then same things we will check for the max. If max is also not true, then we will directly return the none value here. But we have to remember one thing for checking this information, left child and right child. So for this right child, we have to check that this index should not be greater than the total length of the list. So this index should not be greater than the last index of the list. So for example, in that case, so there is only one child of 3. Okay, so we will check only for left child. So if we apply this formula, then the list index out of range error will occur. So we will check this condition. This calculated index for the right child this should be the less than to the last index of our list. So we will compile all these things in our solution code. Then so just explaining the solution for this. Yeah. So this is a main function type of heap. If min heap a equal to true, then we will return min. If max heap a equal to true, then we will return max. Otherwise, return none. And we are creating a min heap and max heap function separately here. So what we are doing in the min heap. So for I in range, len of here what we are doing. So len of a minus 2 load division 2 plus 1. So we can change these things. Actually, we are starting from the last parent from this using this. Okay. So for every parent, we will check if ai. So this is the parent. For here we are checking the min heap. So this is the parent ai, and this is the left child. Okay. So if this condition is true, then we will check the second part. If AI is okay, so and so second condition is coming in the next. Okay. Okay. Yeah. So for min if we are checking for the false case, if parent is greater than for our left child nodes, or if right index is not equal to the length of the A. So here we are calculating the index for the right child. If it is not equal to the length of the A, so 2i plus 1, 2i plus 2. Should be, I think, minus 1, because we are comparing the last. Okay. Okay. Yeah. So if it is greater, for example, if this is equal to the length of the, that means index is out of range. So if it is not equal to 2i plus 2 is not equal to length of the, then we will check the second condition. So we will compare this parent to their right child value. So if parent value is greater than this right child value, so we will return false. Otherwise, we will return true. So in this for loop, we are checking if any sub part of the heap is violating the min heap condition. If it is violating the min heap condition, then we will return the false. Otherwise, we will return true. Same for the max heap. For every parent, we will check if any sub part of the heap, if any of the sub part of the heap is violating the max heap properties, then we will return false. Otherwise, we will return true. So these are two small functions that will return that will check the list is min heap, max heap, or not. So we can easily find out the type of heap using this formula. And next, yeah, so find redundant edge. So this is also a similar problem which is based on the Kruskal algorithm actually. Here what we are asking that write a function find redundant edge. Here edge is given e, and there is one n value that accept an edge e in increasing order of the edge weight, and the number of vertices n labeled from 0 to n minus 1 in a connected undirected graph, and the function returns a list of redundant edges in increasing order of weights. So by removing these edges, the graph should remain connected with the minimum total cost of edges. So minimum cost is connected, so basically. So here actually we are asking to find out the edge which are not part of the our spanning tree. So same things we have already done in the first question. So we will here our edge list is given in the sorted according to the sorted weight. Okay, so we can directly apply this component part of the things of the Kruskal algorithm. We will read edge one by one and then check if edge is creating a cycle. Then we will include in our graph. So sorry, if edge is creating a cycle, we will not include in the graph, and we will include in our output result. Okay. So same thing. So we can solve this using the same method. So I think complexity things is not given. Otherwise, we will apply the union find data structure for that. So I think this you can solve this problem. This is similar to the first problem. Okay, then we will move to the third problem. Week 6, 3. Okay. Write a function find kth largest root comma k that accept root as a reference of the root node of the BST. So here one binary search tree is given of n elements and an integer k where k value is greater than 0 and less than equal to n. The function should return the kth largest element without doing any modification in binary search tree. The complexity of the solution should be in order of log n plus k. So here one binary search tree is given. So for example, so 10, 5, 2, 6, 1. Twenty, 15, 30, 25, and then 40, like this. Okay, so some binary search tree is given, and we are asking to find out the, for example, third largest. Okay, third largest. So first largest is the maximum value of this tree. So this is 40. And third, what will be the third largest? So third largest will be this 25. Okay. So our answer should be this 25. This is the third largest. So first is 40, second is 30, then third is 25. So this is the question from the binary search tree, how we can find this information. One method we can apply, we can traverse this binary search tree according to our in-order traversal. We can apply in-order traversal, and we can read all the value. So we will get a list in increasing order of their value. So for example, if we apply the in-order traversal on that graph, so we will start from the root. So what is the concept of in-order traversal is, we check the left part first. If it is available, then we print the value of node. So for example, this is the print information, then we will move to the right part. Okay, so these L part is and R part are recursive call, and this P is the print information. Okay, so we can apply this LPR formula on from our root nodes. So for example, LPR. So first step is left recursive call, then we will move to the left part LPR. Then first step of this is the left recursive call, then we will move to the left part. Then first step of this is left recursive call, then we will move to the left child. Okay, now there is no left node available, then first step will be skipped, and then second step will perform. So this is the print information. So we can use any operation here. So we can append this node information in our out list at this step. So for example, if we are just printing this, so this one element will be printed, then we will move to the last step. So write recursive call. So there is no node, so this step will also skip. Same, then we will move to the back. So now we will perform the second step of this P. This is the 2, and then write recursive call. So there is no node at the right position, so this will let skip. Then same things, we will perform this print information here. So now 5, then write recursive call. So yeah, there is right node is available. So then LPR will move. Now there is no left child is available. Now print 6 and write recursive. So there is no right available. Okay, so we have already visited this. Now we will move back, then move back. Wow. Okay, so now print this 10, then move to the right recursive call. So we will move to this LPR, then first left recursive, then move to the left, LPR, then there's no left, then print this information 12, then no right, then come back to this, print 15, then move to the right, LPR steps, no left, then print 17, then no right available, then move back, now print 20, and then right recursive pause, so LPR, then left, LPR, then 25, then 30, then 40. Okay. So we can read all the binary search element in this in increasing order using this in order traversal. After that, we can return the third largest element directly. So we can return the third element from the last. So this is this will be the third. So we can apply this method to solve this problem. But what will be the complexity for this is total number of elements n. Okay, but here we are asking the solution to log n complexity. I think log n complexity is there. Yeah, the complexity of the solution should be in order because log n plus k. Yes, log n plus k. So k is also available. So how we can solve this things? Kth largest, yeah. So I'm creating this diagram again. So 10. Take another example. For example, 10, 30, 25, 50, 45, 60, 50, 28, 3, 9, 7. Okay. So, for example, if we are finding a third largest or fourth largest element, so we can directly call. So we can move to the last elements because we know that what is the maximum element is always available at the rightmost side. Okay, so we can start from here and then we can move to the rightmost side. So we can move from this. If right node is available, then we can move. If right node is not available, that means that will be the maximum element. So for we will check for the 30 right children is available, then we will move to the right side. Okay, so now here now we will check right node is available, then we will move to this part. Now there is no right is available, so we can directly return this is a maximum element. Okay, so maximum element we can find by just traversal using in that way. We are starting from the root and we will visit the right part only. After that, we can find out the at the returning time we can find out the this kth largest information. So this is the first largest. Okay, this is the first largest. So after returning time, we can apply this information. So this type of traversing, we will move back to the parent node, and then we will check if there is a left child node is available or not. Okay, so after moving to the back, so for example, we are moving to this. So this is the second. We will take one counter for that. So this is a second largest element. If any child node is available, left child node is available for that, then we will move to this left child, and then we will check is there any node available, a right node is available. So we will move to the rightmost part. For example, 48 node is available, so that will become a third largest. So this type of some addition we will apply at the return type when we are returning from the recursive call. so we can find out the this first largest, second largest, third largest. So I'm just showing the solution for this. Yeah. So here, this is the main part of the function. K, find kth largest root comma k. So we will call this kth largest function on the root. And what we are doing in this kth largest, we are just taking one global counter, count and result. Okay. So count is representing this k value. We will so after reaching the
Root
maximum,
means root here is source vertex.
root is a root vertex of the tree.
Yeah, so topmost vertex.
Yeah, topmost vertex called the root node. No? In tree, there is one top vertex called root. That is the reference of this root. So, sorry. Okay, so in this code, we will take one global counter. So count and result. If and there is one, we have already assigned this value count equal to 0 and result equal to -1. And we check that if root dot right does not equal to null, then we will find out the find kth largest of root right dot comma k. Okay, so we are just applying this kth largest element on the right child. That means we are moving to this right node. So same things, kth largest. Okay. Okay, and we are increasing this counter value here. Count equal to count plus 1. If count equal to k, if any time if count value become a k, then we will return this result equal to root dot value. Return. So at the returning time, we will apply this find kth largest of root dot left comma k. So using this recursive solution, what we are doing, we can understand on this. So we are applying this find kth largest at here first. Okay, so find kth largest, and if right node is available, then we are applying this algorithm at this node. Okay, so fkl. Okay, then if right of this, so same things we will repeat again. So we, for example, now we are finding in that area. So we will applying, if right node is available, then we will apply fkl here, and same things for 60 fkl. Okay, so this is the first recursive call we are getting from here. If this information, so every time after recursive call, we will increase this counter value, count equal to count plus 1. So this value will be increased when we are returning back. So from this last step, so we will return. That means this step is complete. There is no so there is no next node, next right node is available. So second next step will be executed. So this is a count equal to count plus 1. So now our counter will increase from here. Okay, so now our counter will become 1 here. Okay, now we will move to the back. So in our code, so what we are doing, if count equal to so yeah, we are increasing this, then we are also checking this count equal to k. So anytime is if count equal to k, then we will return the result equal to root dot value. So for example, if we are asking the first largest, so at that time we will check that if count equal to k, then we will return directly this 60 value. But if count is not equal to k, then we will perform this operation, and so that means this condition is not true. Then we will check that find kth largest root dot left k. So if root dot left k is not available, so for example for 60, so there is no left is available. So that means no child node is available, so this part is completed. Now we will move to this back part. Okay, now we will increase the counter by 1, so it become a 2. Then we will call the FKL algorithm on this left part. Okay, so FKL. So we will call this find kth largest on this part. Now
After increasing the count, we are checking for the k.
left child, yeah.
No, the parameter k.
Yeah, after increasing the count, right? Because we have initialized by 0. Okay, so after so after recursive call, after increasing the counter, then we are check this information. Count equal to k. Okay,
So where is the base condition over here?
best condition means
Base condition of recursive call.
actually there is no base condition, because here we are checking inside this if this condition is not true, then no operation will be performed. If root dot right
Till
does
the
not equal to
time
none.
it will keep going till the time right node is there.
Yes. So there is no else part for that. So that means this if right child is not available, then this recursive call will be skipped. So we are checking only for when we are getting the right child. We are calling this recursive part. And at the returning time, we are checking this left part. If any node contains the left part, then we are applying this find kth largest on the left node. Okay, so for example, at this stage, so this 50 is a second largest. Okay, but for example, we are interested in the fourth largest. So at the returning time of this, so after increasing the counter 2, then we will check if k our counter value equal to, so for example, k value equal to 4. So our counter is not equal to 4. Then we will check that we will call the recursive on the left child. FKL find kth largest on the left child. So left child is available. Then we will apply this FKL on this part. And after applying this part, so same process will be repeat for, so counter will increase for okay, so right child is also available, then we will move to the right child now, FKL here. And at the time of returning back, so there is no right or no left here. Okay, so after checking the right part, then we will increase the counter here. So this is the third largest value, 48, and there is no left, then we will skip, we will move back to the previous call. So this is the, now there is no left part for that node is, so then that means counter, we will increase the counter for that is, now it become a 4. At that time, we will check that counter is now counter equal to our k, and then we will return this node value. This is 45. So you can see we can, so for example, if our binary search tree is balanced, so we can reach to the maximum value in log n steps. After that, in k steps, we can find out the kth largest steps. Okay, so here 1, 2, 3, 4. So in fourth step, we can find out the kth largest element. So this is the recursive solution to find out the kth largest element. Okay, got it?
Okay.
Okay. So this is the sixth, and fifth problem is simply same solution. You can apply the Kruskal algorithms. If you have any other query and any problem, so you can ask. So now week 6 deadline is extended to 15 June, but week 5 is today. Okay, so if you have no query, then we can close. Okay, thank you, everyone.
Thank you, sir.
Okay.
Thank you, sir.
Okay.